Critical point. So C comma f of C is a critical point if the following two things are true. Number one, f of C exists. And number two, at some point, C comma f of C, f prime of C is equal to 0, or the derivative does not exist at that point. So that is the definition of a critical point. The extreme value theorem states the following. If a function is continuous on a closed interval a to b, so note that this is a closed interval, then the following two things are true. Well, the following thing is true, and then there's a note. So first, f, the function, has both a maximum and a minimum on the closed interval a comma b. And we want to note that these things that are called extrema can occur at the endpoints. So let's briefly talk about what this actually means. If we have some kind of function, and let's take a graph of the function. Say we have the graph of the function, and then here is the value a, and here is the value b. If I have the graph of this function, what this is saying is that f has a global or absolute minimum and maximum on this interval from a to b. So basically what that means is there is a highest point and there is a lowest point on this function as long as this is continuous. So in this particular case, this value would, whatever the y value is here, the y value of this function would be considered the maximum at that point. And then down here, the y value is going to be considered the absolute or global minimum, or what we will call the extreme value, the absolute minimum in that case. Now, like it says, it is possible that it could be the endpoint. So if I just change this graph slightly, and I make it look like this, and I move B slightly to the right, then I no longer have the absolute max where it is. I would have to relocate the absolute max up here. And sorry, y value is still true. It's just off the screen now. The absolute max value is, sorry, B was a little bit off, but the absolute max value is now located at the endpoint because that is higher than this hump right here, this little curvy thing where it starts going back down. And we'll get a name for that in a minute. But notice that we're just taking whatever the highest value is on the interval a to b. First derivative test. If f prime is positive to the left of a critical point at x equals c, and negative to the right of the critical point at x equals c, then there is a local maximum at x equals c. So basically what that looks like is if I have some point, x equals c, and I know that f prime of x, so that means my derivative. So if I have the derivative f prime of x, and I know that the derivative is positive to the left of c and negative to the left of c, or negative to the right of c, let's think about what that means for my function. So if I have the graph of f of x, if f prime is positive, that means that the slopes of my tangent lines are positive, which means my function is increasing. So my function is increasing. And then at some point c, it ceases to have an increasing function. It ceases to have positive slopes and starts to have negative slopes. We call this a local maximum. So we have a local maximum if the derivative is positive to the left and negative to the right of some function. Likewise, if f prime is negative to the left of the critical point and positive to the right of the critical point, I have a very similar situation, except we're going to call it a local minimum. So if I have, again, a little chart of f prime, and it's negative to the left and positive to the right, if I take a look at the graph of f of x, that means we're going to have at some point C a spot where my function, since f prime is negative, that means that the slopes of my tangent lines are negative, which means that my function is decreasing. And then all of a sudden, oops, my function starts increasing. So I have a situation where it looks like this. So I have my function has a local minimum. So if I'm looking at, once again, the local maximum, it appears that everything to the left in a small area, so if I zoomed in on that box real far, real tight, everything to the left of C is going to be going up, and everything to the right of C is going to be going down. That's what a local maximum is. And if I zoomed in on this box real close, notice that everything to the left of C is going down, and everything to the right of C is going up. So basically, that's the lowest value in that box. And if I zoomed in real tight, everything to either side is going to be above the value at C. Back up here, if I zoomed in real tight, everything to the left and right of C is going to be below it. That's why we call that a local maximum. Concavity. The graph of a differentiable function, y equals f of x, is concave up if f prime of x is increasing on the interval. Sorry, forgot to put the pen down. And concave down if f prime is decreasing on the interval. So, a couple pictures just to make sure that we understand what's going on. If f prime is increasing, that means that the slopes of my tangent lines are getting more positive. So that means if my function is decreasing, if my slopes are getting more positive, that means that my slopes are kind of leveling off. Likewise, if my function is increasing, that means my slopes are getting more steep. So in either case, if I'm decreasing, my slopes are leveling off and getting closer to zero. If I'm increasing, my slopes are getting bigger, steeper. Notice that this is a graph that is concave up. Down here, if f prime is decreasing, that means that the graph will look something like this. Therefore, if my graph is decreasing right here, my slopes are getting more and more negative. If my graph is increasing, my slopes are leveling off and becoming closer to zero. So that's what a concave up and a concave down function look like. Notice that something is concave up if water can be held inside of it. Something is concave down. If water was getting poured down, it would kind of run off the sides. So concave up looks like a cup. Concave down looks like a bowl, basically, where the water is going to run off the sides if the bowl is upside down. Okay, now can a function be both at different spots? Yes. So if we have a function that looks like this, we have a function that appears to be concave down until about here. And then at that point, it starts becoming concave up after that. So this would be concave down over here, and this would be concave up over here. Second derivative test. If f prime of c equals 0 and f double prime of c is less than 0, then f has a local or relative maximum at x equals c. If f prime of c equals 0 and f double prime of c is greater than 0, then f has a local minimum at x equals c. We already did the first derivative test, and we kind of talked about why there would be a local max or a min at certain spots. But let's talk about why the second derivative test might also be able to help us at some point. So if the derivative equals 0, that means that there's a horizontal tangent line. So for example, let's take a look at this function. So we have a function that looks something like this. I have 3 horizontal tangent lines that I can see. If I'm looking at this problem, and I look at 3 horizontal tangent lines, so I have the derivative equal to 0 3 times. If I look at this spot, notice that the function in this case is concave up. That appears to be a local minimum. If I look at this spot, that is also concave up, which means that my second derivative is greater than 0. Just based on this picture, it's a local minimum. If I'm looking at whether something could be a local maximum because I'm concave down and I have a horizontal tangent line, my derivative is equal to 0, that would be this situation. So that's kind of what a picture would look like. This is a little bit confusing for some people because we have f prime is less than 0 means maximum. And some people that like to memorize things always think that less than should mean minimum. But if you understand the concept and what's going on in the picture, it makes a lot more sense. A point of inflection is a point on a curve in which the concavity changes. So we've already seen a graph of this, but if I have something where my graph may look something like this, we're concave up over here, we're concave down over here, and then at some point, it changes from concave up to concave down. That point is called a point of inflection. So any point where it changes from concave up to concave down or concave down to concave up, that's called a point of inflection. Inflection points may be stationary points, but they're not local maxes or mins. So an example of that would be y equals x cubed, where we have a graph that looks something like this. Notice it changes from concave down to concave up. And it's the derivative at this value is also equal to 0. So f prime of 0 is 0, but it's not a local max or min because if I take a look at the first derivative test, so I called this f of x, which is x cubed. If I take a look at this, f prime is 3x squared. If I make a little chart of f prime, notice that the derivative is always positive. So that means I don't have a local max or min at that point. So I can have a stationary point, quote unquote, but it's not a local max or min. A stationary point, in essence, meaning that my derivative is 0, so I'm neither increasing nor decreasing. Note, sign charts are not acceptable as justification on the AP exam. So what I just did, where I gave a sign chart, this is not acceptable as justification on the AP exam. So I'm going to give a brief example of what would be good on the AP exam. Example, f of x equals x squared plus 2x minus 3. I've put the graphs on the paper as well, just to make it a little bit easier for us. So if I'm looking at the derivative function, notice that at -1, the derivative changes on this problem. I guess I should take the derivative and just make sure that we're aware of what's going on. 2x plus 2. So if I set 2x plus 2 equal to 0, that means that x equals -1 is the value where f prime of x equals 0, which I can see from the graph. So if I'm looking at this, I might go negative, positive. One thing that's really important to note is that I did not label my mini graph. So if I don't label my mini graph, the AP graders will never even look at it. They have no idea what you're talking about. So It's better, like they don't know if I'm talking about f of x, f prime of x, f double prime of x, anything. So I definitely have to label my graph f prime of x. That at least tells them that you're doing something with the derivative. But that doesn't give them enough for you to talk about justification. So if the problem is asking for what the uh, what the for example, is there a local minimum or a maximum or something? I can tell that there is a local minimum at x equals -1 because f prime changes from negative to positive. That's actually what you have to say. So if you want to say f of x has a local minimum at x equals -1, you have to indicate because f prime of x changes from negative to positive at x equals -1. That would be justification. So you can use the chart to help your thinking, but you must give justification in some sort of concise sentence that explains the mathematics.